right, so with greatest common factor, there are two methods that we can use when finding the greatest common factor. But before we look at the two methods, we need to look at the definition of a common factor. What is it? Well, it's a whole number that is a factor of two or more non-zero whole numbers. So it's, say you take the numbers 12 and 16. Well, 12 and 16 both have a factor of 4, so that's a common factor. So we're either looking for common factors or we're looking for common prime factors in both of our methods for solving GCF. So let's look at our methods, okay? You need to have these two methods listed in your notes. So if you didn't get that in your notes on Friday, you need to make sure that you list the two methods. If I were to make that a short answer question on a quiz or a test, what are the two methods for finding GCF? You should be able to say listing factors and prime factorization. Those are my two methods. So with listing factors, it's exactly what it sounds like. I need to list all of the numbers that can be multiplied together to equal that number, 3 times 4, until it repeats. 1 times 30, 2 times 15, 3 times 10, 5 times 6. Okay, of course the next one is 6 times 5, that cancels, and same with this one. The next one's 4 times 3, so that cancels. All right, so as soon as they repeat, I know that I'm done, and I can list my factors. 1, 2, 3, 4, 6, and 12. And for 30, 1, 2, 3, 5, 6, 10, 15, and 30. So if I'm trying to find the greatest common factor and I have listed my factors in this way, all I have to find is the largest number that is a common factor between the two of them. And what number do you see? 6. You see a 6, okay? You've got a number larger than 6 in the first one of 12, but 12 is not a factor of 30. So 6 is my GCF. I'm just going to write it right in between these two numbers. GCF is 6. GCF is 6. When I'm listing factors, that's my endpoint as soon as I find the largest factor. But when I'm doing prime factorization, and I'm doing my upside down division, I think you guys already have these numbers factored, right? You guys already have this in your notes? Is that correct? Okay. All right, so we do the upside down division. And here's why, okay? This is our biggest reason, and we're going to talk about, the frequency that we would use listing factors versus prime factorization. But prime factorization is very practical when I'm factoring really large numbers. You would agree, guys, that listing factors for 960 would be like ridiculous, right? That would take forever. So listing factors is really only practical when you have small numbers. All right, now that I have done my prime factorization, I want to list my prime factors. 2 times 2 times 2 times 3 times 5. And for 960, I've got 6 2's. 1, 2, 3, 4, 5, 6, a 3, and a 5. All right, so now do y'all remember what do I do next? Yes, I group them. And I do that by drawing a line through each pair of common prime factors. All right, so that's different than just common factors. These factors are prime numbers. So I draw a line through each pair of common factors, and I write each one of those numbers one time in my GCF. Equals 1, 2, 3 2's. Why 3 2's? Because there's 3 sets, right, that I identified as common factors. How many 3's would I write? One 3. There's only one set of 3's. And how many 5's? 1. And when I multiply those numbers together, what do I get? When I multiply all those numbers together, 120. Now, it won't always work out that the GCF is actually the smaller of the two numbers. You see how this is 120 up here? That's not always going to work out. That's more or less a coincidence. But what I want you to see is this. When I'm listing factors, it is a practical method to use when I am factoring or finding the GCF of small numbers. So if I were to give this a percentage, I would say that I would list factors to find GCF about 10% of the time. So the greater majority of the time when you're finding GCF, you're going to use prime factorization. You see the breakdown? And here's another thing to consider. With prime factorization, this method works every single time, even if you're using small numbers. So if you just want to rely on one method versus the other, prime factorization is where it's at. Actually, in Algebra 1 and Algebra 2, they might not even teach you listing factors. They may, but they're not going to place a huge emphasis on that method. All right, so if you want to pick a favorite, your favorite needs to be prime factorization. All right, the larger numbers will be a nightmare if you try to do the listing factors. So that's just my advice to you. On your homework tonight, it is not going to specify which method you need to use. You can do whichever one you want, but that's my advice to you, is to do the prime factorization. All right, any questions so far? Anything at all? Okay, so two methods, we took care of that. Now I want to find the GCF of three numbers. Okay, so we have 16, 32, and 40. These numbers are new. We didn't do this on Friday, so I need everybody to do the GCF of the three numbers. I'm going to let you choose which method, but I'm going to do prime factorization. Okay, so if you want to do listing factors, you'll end up with the correct answer. I can come over and check your work, but for time's sake, we're just going to do prime factorization on the screen. All right, prime factorization of 16. Lots of twos, right? 32, even more twos. 40. Okay, so now I'm going to list my prime factors. 2, 2, 2, and 2. And for 32, 2, 2. And for 40. Okay, so in order for it to count as a set, it has to be a factor in all three numbers. So I have one set, two sets, three sets. Any others? No, because yes, the twos are common here, but that's a 5, so that doesn't count. All right, so in my GCF, I have 2 times 2 times 2, which equals what, guys? 8. All right, raise your hand if you got 8. Did you get 8? Okay, very good. All right, so the biggest thing you need to remember about GCF of three numbers is it must be a factor in all three numbers to count as a set. All right? Okay, so that's GCF of three numbers. Let's talk for a minute about relatively prime numbers. So sometimes when you do the prime factorization of two numbers, they're actually going to have no factors in common. Two or more numbers are relatively prime if they have no factors in common, and I'm going to add other than a 1. Because 1's my gimme, right? Like any number has a factor of 1. So if they have no factors in common other than the number 1, I would identify the GCF as 1, and I would say that the numbers are relatively prime. All right, so if you get to the prime factorization, and I have this happen every year, okay? You get to the prime factorization, you notice that there are no factors in common, The GCF is not 0, okay? It's not 0. It's never going to be 0 because it will always at least have a common factor of 1. But if the greatest common factor is 1, we call the numbers relatively prime. So let me ask you this. What if my GCF was 12? Are the numbers relatively prime? No. So on your homework tonight, it's going to ask you, are they or are they not? If your GCF is anything but 1, you're going to say not relatively prime. Does that make sense? Okay, you think that that's kind of obvious, but you know, sometimes we kind of overlook that part of the directions on the homework. So just go ahead and finish writing that down. Okay, so now let's do the GCF of these two numbers. One of the questions is going to be relatively prime. The other one is going to be not relatively prime. So let's see how it shakes out. Okay, so we're going to do the prime factorization of 28 and 84. And then we're going to do the prime factorization of 224 and 243. All right, and when you do the prime factorization, you'll have common factors in one of the numbers, and you'll have no common factors in the other one. All right, so let's go ahead and work these two questions. Okay, so we've got 2, 14, 2, 7, 2, 42, 2, 21, 3, and 7. All right, so for 28 and 84, we have prime factors of 2, 2, and 7, and 2, 2, 3, and 7. So we got 1, 2, 3 common sets. So our GCF is 2 times 2 times 7, which is 28. Clearly not, and we're going to call it RP. Is that okay if we abbreviate relatively prime? Yes. GCF is 28, not relatively prime. So I'm kind of giving it away, but this one, 112. 2 goes into 112. How many times? 56, correct, yeah. 2 into 56, 28. 2 into 28, 14. 2 into 14, 7. 243, 3 goes into it 81 times. 3 goes into it again 27. Looks like a bunch of 3s to me, huh? Okay, so you can kind of just start even looking ahead. 224, you've got a bunch of 2s, 5 2s and a 7. 1, 2, 3, 4, 5, and a 7. And for 243, you have a bunch of 3s. 2, 3. How many 3s was it? 5, 4, and 5. So there's nothing to match up. There are no common factors. So my GCF is 1 because every number has a factor of 1, and I would say they are relatively prime. So on this section, when it says tell whether or not they are relatively prime, you either need to say relatively prime or not relatively prime. So you're finding the GCF of both. Any questions here on identifying relatively prime numbers? All right, are y'all getting the hang of that prime factorization a little bit better? Good. So let's talk about monomials and the GCF. A monomial, we learned, is a number being multiplied by a variable, can be raised to exponents, that's no problem. All right, so we're going to look at finding the GCF of these monomials. We talked in 4.1 about the fact that we have to do the prime factorization of the numbers first before we can break down all of the factors. So go ahead and do the prime factorization of 18 and 28. Go ahead and write it how you see it written up here on the screen. All right, 2, 3, and 3, 2, 14, 2, and 7. All right, so now when you list these factors, I want you to write the entire monomial, 18xy squared. Now let's break it down. We're writing everything in expanded form. 2 times 3 times 3 times How many x's do you see there?
1.
You see 1x and how many y's?
2.
2 y's. Okay, so now we've written the whole thing expanded. And then 28x squared y squared is 2 times 2 times 7 times x times x times y times y. All right, so now we're going to identify the groups. We have one set of 2's, one set of x's, and 2 sets of y's. So now in my GCF, I'm going to write each common set one time in my GCF. 2 times x times y times y. And I want you to write it expanded first so you can make sure that you're representing each set one time in your GCF. But now we can write it back in exponent form, and what would it be? 2xy squared. Okay, so now I want you to do the second one on your own. 14s to the third p and 21sp squared. All right, go ahead and do the prime factorization and find your GCF of the monomial. All right, so 14, 2 and 7, 21, 3 and 7. All right, so now I'm going to do my listing my prime factors. 14s to the third p is 2 times 7 times s times s times s times p. And then for 21 sp squared, it's 3 times 7 times s, and how many p's?
2.
Okay, so now let's pair them up. 7's S, P. All right, so really, can I just write my GCF? I don't have to write the multiplication part. I mean, it's pretty obvious because there aren't any repeated that my GCF is going to be 7SP. Okay. So, you know I just said you need to write the expanded form, and I know that part is important, especially when you have things repeating. When you don't have any factors repeating, I don't mind if you just write 7SP, but you just need to be careful. So you might not get a deduction for not showing this step, but it is a really good idea, especially when you have repeated factors. Does that make sense? Okay, so if you understand that, that's everything you need to know for this section 4.2.